Good morning, everyone. My name is Midhun Somasundaran. I'm here today with Kumar from Broadcom and my colleague Shrikrishna Khare. We are going to talk about how we used fungible tables in SAI to address some of the traffic engineering challenges that we faced in our backend AI network to address some of the AML application requirements. So here is the agenda for the talk. First, I'm going to provide an overview of the use case, the solution that we came up with, and some of the challenges that we faced in SAI. Jay is going to talk about some of the hardware features that made this solution possible and some of the enhancements that were done to the SAI spec. Shri is going to cover FOS as a case study for implementation and rollout of this feature, and is going to cover the call to action also. Let's get started. So HPC training jobs, they process large amount of data, and they run on more than one GPU racks. So if you attended the presentation on Tuesday about evolution of Meta's AI network by Omar, you would know that we have jobs of different sizes at Meta, like AI jobs. So these range from ranking jobs, which are ads ranking or newsfeed recommendation ranking jobs that run on 32, 64, 128, or 256 GPUs on the lower side. And on the far end, we have on the far end, we have large language training models which run on 32K or 64K GPUs. So the use case we are looking at here is the former one, which is the ranking jobs use case. So an HPC job scheduler is the one which is in charge of allocating the GPU racks for the jobs whenever a user makes a request. So think of this like a cloud service for running the AI training jobs. So each of the square that you see in this diagram is a GPU rack, and the whole diagram is showing a cluster of GPU racks. So once the scheduler allocates the GPU racks and the jobs start running, we are going to see the network traffic coming in. And this traffic is low entropy, it's bursty, and it's mostly made of elephant flows. So these are basically Rocky V2 RDMA traffic, which is going to a fixed UDP destination port. These jobs require that the network be a non-blocking and a low latency network. Otherwise, you are going to have long job completion times or timeouts happening. So imagine like 50 to 100 jobs are running anytime on a cluster, and we have to provide a non-blocking network fabric for this service, and it's quite challenging. Let's take a closer look at the training job to understand the traffic pattern a little bit. Each training job has a large input sample set and an expected output. The goal of the training job is to minimize the difference between the computed output and the expected output. So the data is in the forward pass, the data is fed through the neural network, and each of the GPU computes an error function. So the data cannot fit into one GPU, so it has to be sharded across all these GPUs. So in the forward pass, the GPUs exchange all-to-all information, like they exchange all-to-all traffic to embed this data into each of these GPUs. So once the data is embedded, the GPUs compute the weights of the model, and then in backward pass, they adjust the weights among themselves. So there are two traffic patterns here, which is all-to-all and all-reduce. And this keeps repeating multiple times over the life of the job. Now, one thing to note here is that the GPUs, the job can proceed only to the next phase only after all the GPUs are done with the current phase. What that means is that if there is a missing ACK or a delayed ACK, that's going to impact the whole job completion time or even result in a timeout. So here is a look at the backend network topology that we use for running these kind of jobs at Meta. So each rack has 2 hosts. Each host has 8 GPUs. The GPUs are connected to the rack switch using 400G links. There are 288 such racks. And these racks are connected to each other through cluster switches. So there are 16 cluster switches, and each of the rack switch is connected to all of these 16 cluster switches. So as you can see, there is a lot of symmetry in this network. So every GPU is 1 host away. So that gives us some advantages. So combine the fact that the network is very symmetric and the jobs are going to produce either all-to-all or all-reduced traffic at the same time, like at a given point of time, we realized that we could provide a reasonably non-blocking fabric by pinning some of this egress traffic to specific paths instead of using ECMP. So in this example, all the odd numbered, the traffic going to all the odd numbered host GPUs are pinned to the first 8 links, and the even numbered GPU hosts are pinned to the second set of 8 links. So why does this work? Such a simple scheme works because each GPU can source or sync only 400G at a point of time. The network is symmetric, and the traffic is going to be either all-to-all or all-reduce. So, of course, this will have limitations. So the first limitation is in scheduling the jobs. So if you schedule the jobs using partial racks instead of a full rack, then this static pinning doesn't work properly. In this example, all the traffic that is going to host 3 and host 5, and that is originating from the rack switch 1 will get pinned to the first 8 ports, and that will create congestion. And obviously, like if there is a port failure or a link drain, the traffic that is pinned to that port is going to be distributed among the remaining links, and that's going to introduce inconsistency in the traffic pattern, and that's going to, like the job completion times are going to suffer as well. So the solution that we came up at Meta is to use a controller. So the controller listens to the placement information from the scheduler. Now, with this information, it can predict what is the traffic that's going to happen in the network. It uses this information along with the topology information that it gets from the routing protocol, which is OpenR in our case, runs a constraint shortest path first algorithm, and then determines the optimal path by taking into consideration the load on the network. So to implement this solution, we need ability to forward large amount of flows based on source and destination pair of prefixes instead of doing destination-based forwarding. So we looked at the options that are available in SAI and in the pipeline. So the first option is TCAM. TCAM can override the LPM decision, but TCAM has limited scale on many chipsets. So we looked at, the next option that we looked at is hash table or exact match. The exact match result can override the LPM result. And in our use case, TCAM overrides the EM result, although we like this ordering to be flexible. The second limitation that we encountered was that the SAI pipeline does not have support for exact match. There is no way to specify that a table is exact match. We cannot specify the relative ordering between exact match and TCAM, and we cannot specify the properties of the exact match. So Jay is going to talk more about how these limitations were addressed in the next set of slides.
Thank you, Midhun. So before I go into the details of the specification itself, if you see what's happening, the innovation in the space of the application, the AML space is happening so fast. And to keep up with that innovation, hardware is also trying to innovate. So we are, as a silicon vendor, making improvements in the hardware design, chips. And then once the hardware is designed, we need to also improve the size specification. So for this feature, as Midhun mentioned, that key information which was needed was the exact match. So that is one hardware kind of application which was there. But the other, once we have that ability to do exact match, there are other things which are also needed. So what we did a little bit of a forward-looking enhancement to the spec, which includes that you can have fungible tables, because when we define in hardware is a little bit forward-looking. We don't want to get locked into a certain kind of a pipeline. So we put tables, multiple tables, thinking that, oh, maybe application will use like this, like that. Problem that it poses is that how do you define into Psi pipeline? Psi pipeline, as we know, is an abstraction. And it's a very deliberate abstraction where we abstract any vendor-specific constructs in the Psi logical pipeline. We do not want to expose anything which is vendor-specific. So that brings its own challenges. So that's number one. Number two is that the pipeline itself should not be complicated. It should be easy to program. So we have to worry about that. So what we did, the basic requirement was on the exact match, which essentially looks like very much like ACL table. It has a match criteria, which we call as a Q set. There are a set of actions, except that there is no mask. So we take any key does not have a mask. It's an exact match lookup. And the hardware implements it as a hash table, right? So today, Psi pipeline supports multiple stages. So today there are 4 stages of ACL which are supported. So maxsec, which is a maxsec stage. There's a pre-ingress which happens before we do the L3 lookup. So we can define our match criteria. Again, there's a TCAM lookup. And then there's an ingress stage, which is after the L3 lookup. And then there's an egress pipeline, which we call as an egress stage. So one option we had that we can take all these fungible hardware, discuss among silicon vendors, and keep on creating more and more of these stages. So that was one way to approach it. That's non-scalable, right? First, as a silicon vendors, we cannot come to an agreement that this is the right place to put this hardware block. And second is we make the pipeline really complex. It has a lot of stages in that. The second problem is that today, the concept of lookup, which happens at any stage, is basically I can do a parallel lookup. So the TCAM has slices. We can do a parallel lookup. Or there is an old method which was defined, which says sequential lookup. And sequential lookup does not mean that all the slices are looked sequentially. It means that you start sequentially, and the first lookup where we hit the match, the key, the lookup stops. It does not go beyond that. We wanted something a little bit different for this use case. We wanted where lookup happens in a table. We take the output of that lookup and feed it into the next table. And we can create a continuous chain of n such hardware blocks. So to do that, what we created, now it's a little bit not easy to explain in 3 minutes, but I'll try. So what we created a concept of chain groups. Chain groups is nothing but a software abstraction which gives a soft representation of a hardware. So in a chain group, we are able to define that what kind of table groups can be a member of a chain group. So today, table groups are type sequential or parallel lookup. And we can say within a chain group, all the tables which are there can either be a sequential or parallel. We can mux it, but we don't like to. So that's one way to abstract it. Then also we have to define a priority. When the sequential lookup or the chain lookup is happening, we want to know that which lookup should happen when. So there's a concept of priority which is introduced. And lastly, that how do we know that what hardware supports? So there is a whole infrastructure of capability which we do. And that capability basically tells that how a given hardware supports a set of such stages and what's the priority among them. So this is a high level relationship within the Psi. So if you see, there's a table group which is existing. Table group have members, which is also existing object. And what we have created a concept of chain group. And chain group, as I said, is a soft property. It's a soft object, soft representation. And it is pointed by multiple table group members. and each member can only be part of one chain group. So that's certain restrictions we have put. And if you look, the way this is going to represent in hardware is like this, like what I have shown here. So chain group 1 is consisting of 2 tables, and there's a priority among them, so it comes in the hardware before. And then the table 2 and 3 and 4 comes as a separate. But the beauty of this proposal is that we have not added a new stage in the SI pipeline. It still stays in single stage, which also means it's backward compatible, ISSU works, warm boot works. So that was the key part. I know this is a little bit rushing into it, but that's what it is. This PR is already merged in the main branch. We have done the changes. I'll give from this on to Shri that how this is being used in the actual application. Thank you.
Sure. Thanks, Shri. So Midhun talked about the TCAM scale limitation as well as size spec enhancements and rather size spec gaps. And then Jay covered the size spec enhancement we made to address those gaps. And we'll try to piece it together now. If you look at the diagram on the right, then you will see that there is single ACL table group, which comprises of both TCAM-based ACLs as well as exact match ACLs. And this is sort of held together by having them into different tables, but the tables in turn belong to different chain group. One chain group of type TCAM and another chain group of type exact match. In the next few slides, we'll try to take a concrete example and illustrate how we can work our way towards a model like this. We'll take FBOSS NOS as an example for this. So FBOSS stands for Facebook Open Switching System. It is Meta's software stack for controlling and managing network switches. It's deployed heavily in Meta's data centers. It's one of the largest services in terms of number of instances in Meta's network. Here is a quick sort of insight into how this looks like. So we have hierarchy of switches right from TORs to aggregation level, and FBOSS runs in every role. The same set of binaries run on every role, but what is different is, of course, the configuration, because as you can imagine, the feature requirement for each of these roles is fairly different. So we use config to selectively enable and disable set of features that we want to enable for that specific role. The warm boot upgrades, which is the hitless upgrade, basically you can upgrade a binary without disrupting network traffic, is quite critical for us because a significant fraction of these devices is top-of-the-rack switches, and they don't have any redundancy. And we upgrade them fairly often. So the way to upgrade those is not to take them out of production for maintenance, but instead support this warm boot upgrade mode. And we'll talk more about this as we talk about exact match. It will connect back to this. Here is a quick look at a very high-level FBOSS architecture. There are 3 blocks. If you look at it, the top block is the FBOSS binaries. Middle layer is the vendor SDK. FBOSS uses SI, so that's the SI implementation. And then the forwarding ASIC at the very bottom. At a very high level, the way this works is that config, if you recall I mentioned, is very specific to the switch. The config is fed into software switch, which will convert that into what we call as a switch state, which is an in-memory representation of the config that we want to push out. And the switch state gets sent to the SI switch. And from SI switch perspective, it gets a series of switch states as the state changes in response to a config change or in response to any events that we might be handling. SI switch is responsible for programming the delta. It programs the ASIC, but first it needs to do a delta computation to figure out what changed. And then it will make the appropriate SI API calls, be it add, remove, or set, and program the ASIC. Again, this is connecting back to the slide that we presented earlier, where this is the traffic engineering solution, and the box at the right bottom, highlighted as FBOSS, is the piece that we are zooming in now and talking about how it is implemented to provide the mechanism that we desire for this traffic engineering use case. So this is a sample example where how do you get from the current state. So in this particular example, we have single ACL table group bound as switch ingress, and it has a couple of tables. Let's say one for quality of service use case, another for counters. The reason you cannot place these ACLs into single table is because the way the programming model works is that if you want single packet, to have hit multiple ACL entries, then you have to place them in different tables. That's just the Psi programming model as well as how ASIC support it. So in this case, we want, let's say, QoS as well as counters implemented using TCAMs, part of two different ACL tables. From this state, we want to go to a model which is the first step. Eventually, we want to build our way towards adding exact match, but the first step is just enabling this chained group construct. This is a purely software change, like no hardware programming involved. It's a software construct that gets created and prepares us for the next eventual step. This step can happen on warm boot again, so no disruption to traffic. And we also support rollback. Rollback, we don't do often, like usually we fix forward, but there are cases where if something goes wrong, we want to go back to the previous sane state, then we can go ahead and disable a feature, in this case, for example, and go from step 1 to the before state over warm boot. So if we keep going with this, right? So let's say step 1 is where we are, and now we want to go to the next step. So in the next step, the step 1 has this chain group with TCAMs, and step 2 ends up introducing another chain group. Now you have your ACL tables for QoS and counters, but you also have a new state, or rather a new chain group and new exact match table added, again over warm boot. You can also do rollback on that. And once it gets added, then now the controller can come in and it can dynamically add or remove entries to introduce and implement the traffic engineering solution that we want, that we desire. Now, just talking a little more on the use case front, right? So our fleet, you can think of it like split between devices that support AI use cases and fleet of devices where we do not support or we don't have a need for AI use cases. Now, for a fleet that requires this AI use cases, this is a must-have. We need to have traffic engineering solution for reasons as Midhun explained before. For there, we identified the gap, we bridged the gap. But we did not stop there. There are a couple of reasons why we want to enable this feature even on fleet of devices where we do not need AI support. One is, of course, consistency, because it's easier to manage as against sort of spreading if-elses across the code. Consistent config, have chain groups everywhere. And the other is enabling future use cases. So for our immediate use case, we don't have a use case for chaining. We want to enable exact match. But the moment you add this construct, now it's possible for you to have one ACL entry output feed into another ACL entry and sort of start chaining those. Once we roll it out, it not only makes the config uniform across the fleet, but it also keeps a config-only change in case we want to leverage the chaining aspect of it. Another way to look at this is that if you go back in time, right, like initially Psi only had ACL table support. It still works today. Like you don't have to create table group. You can create ACL table. You will have multiple entries, but as I mentioned before, you cannot have single packet hitting multiple ACL entries if you have one table. So ACL table group takes you one step further. It makes more use cases possible. Think of chain group as sort of an evolution to generalize it even further, right? Not only can you hit multiple entries for same packet, but you can also start chaining them, or you can also start leveraging tables other than TCAM. Here's a quick look at how the performance numbers look like if we implement exact match. So on the x-axis, we have network capacity. Y-axis has the job completion time. The blue and yellow bars are talking about adaptive traffic engineering versus deterministic path routing. You will see that with perfect scheduling, the job completion time is kind of similar, even if the network capacity changes, regardless of the scheme that is being used. But with imperfect scheduling, deterministic path routing, the job completion time just keeps getting up. So you need adaptive traffic engineering if you want to maintain the job completion time, even in the event of network capacity changes. So that takes us to call to action. So as Jay mentioned before, there are several PRs that we worked our way with community on these. These are all merged. Request folks to take a look at them. Another call of action is that explore what chained ACL table groups can offer. It is possible to enable these over warm boot without disrupting traffic, and it will help you unlock wider use cases, be it about leveraging hardware capabilities like exact matches or ability to chain, which has its own benefits. And that's also our last slide. Happy to take questions.
Two questions.
Sure.
So one is routing related, another MPI. So when there's a failure, I assume you are only computing one primary path, you are not computing back of the primary. So if your primary path goes away, you fall back to a CMP. OpenR will take, what, second to update controller. Controller will take another second to compute new topology. Streaming is somewhat slow. So you're 2-3 seconds on the CMP, which is T-unaware. Is it acceptable? Do you see any issues with that?
Yeah. So when if a link goes down, the agent that is running on the box, it reacts immediately. Like we have several layers of reaction. So the first level of reaction is that the agent in the box, it reacts in like 10 to 50 milliseconds. It can react and invalidate these entries. So once the entry gets invalidated, it takes the backup path, which is ECMP. In ECMP, we are using QPair-based hashing. So our ECMP is also pretty good. Like even though the flows are like elephant flows, like we try to like have multiple QPair sessions between the host and then kind of put some entropy into the traffic. So the ECMP, it doesn't degrade it much. Like there will be a slight degradation, but not a lot. Another thing is like after that, then the controller will get notified that the link has gone down, and then it will react and provide an optimal path, program an optimal path. One thing that I want to highlight here is that it's not the unexpected link faults that were trouble for us. Like we can, like it happens rarely. It's not very common, but the most common scenario is drained links for maintenance. So we could have links sometimes drained for a couple of days also, like it could happen, or drained devices or drained links. So that's where our biggest win was with going with a centralized controller.
So in other words, you're fine with 3-5 seconds doing ECMP?
We are fine with a couple of seconds of ECMP with the QPair hashing, QPair based hashing.
Looking up QPair and BTH?
We are looking at the QPair in the packet and computing the hash for ECMP using that QPair also included.
So if I may add, so SAI supports UDF-based hashing, and in that case, we take a UDP desport, which is Rocky, and then the Rocky BTH header, get the QPair.
Okay, so you're just using fixed offset?
Correct. So
let's give some time for others to ask questions too. Thank you.
Short question. So, Nickel, since some time allows you to do link aggregation over NVLink and spray packets across all NICs from one GPU. Wouldn't it help you to do this?
We have different types of use cases. So we are this is very specific to the running the AA job kind of, AA as a job as a cloud service kind of topology. And this is very specific to the small number of GPU jobs, 32 to 128, 256. The technologies that you are referring to, we are using them in addressing some of the other scenarios. So eventually, some of this will get unified, but this is where we are in our evolution of the network.
Thank you.
Very nice talk, Midhun.
Thank you.
I didn't expect that you associate this fungible keyboard for that long. And like two questions. One is how quick you can flush your ACL table. So if you can share that one. The second question is like how often you flushing it, because you say scheduling the job. So I want to see that it's at the very beginning of scheduling the job, or on each of the phase you have to flush your tables.
Yeah, good question. So one of the advantage that we have is that the scheduler, the job scheduler, is talking to the traffic controller. So before the job scheduler actually starts the job, we already know that such a job is going to get started. So the controller can pre-compute this flow paths because it knows that the traffic is going to be all to all or all reduced, and it knows exactly where it is going to come from and where it's to end. So it can pre-compute this path and program it in the hardware. So the speed at which we can program is not hurting us by a lot. So we did some benchmarking with around like 9,000 entries. We are taking around like 4 seconds to program the table, the complete table. So it hasn't been a big concern for us now. And flushing, when we are flushing, we keep track of which entries are going against what port, and we flush only those entries. We don't flush every entry.
Thank you. Apologies. I don't think we have time for more questions. Yeah. We need to.
You guys are a sponsor of UEC QDS, I believe, right? How does this fit into the context of that?
I'll take that. So, we are talking about all these hardware enhancements. In UEC, we are still discussing that how the adoption will come, and we will have an update based on the UEC on that. But there is a thought. Yeah.
Thank you.
Thank you.